For task 1, we generate sinusoidal signal using MATLAB. The signal parameter were amplitude equals to 5, frequency equals to 2 kHz, time duration from 0 to 1 milliseconds, sampling frequency of 100 kHz. Using this parameter, MATLAB generated a clean sinusoidal waveform. Since the frequency is 2 kHz, the signal period is 0.5 millisecond, meaning approximately 2 complete cycles appear within the 1 millisecond observation window. For task 2, we visualize the generated signal using two MATLAB functions, which is a plot and stem. The plot function displays a smooth continuous representation of signal, while the stem function displays discrete sample point. These two visualizations help us understand the difference between continuous time and discrete time signal, which is an important concept in digital communication system. Time domain representation. This slide shows the result of task 2. The upper graph displays the continuous sinusoidal waveform generated using the plot function. The lower graph shows the signals represented as discrete sample using the stem function. We can observe that both graphs represent the same signal, but the stem plots clearly illustrated the individual sample values collected by system. This demonstrates how analog signals are converted into digital sample for processing. Task 3, FFT analysis. For task 3, we use the fast Fourier transform or FFT to analyze the signals in frequency domain. FFT converts a signal from time domain into frequency domain. This allows us to convert a signal from time domain into the frequency domain. This allows us to identify the frequency component contained within the signal. The MATLAB code calculates the FFT and generates the frequency spectrum of the sinusoidal signal. Slide 6. Frequency spectrum of sinusoidal signal. This graph shows the frequency spectrum obtained from the FFT analysis. We can see the dominant peak located at approximately 2 kHz. This matches the original frequency of the generated sinusoidal signals. There are no significant peaks at other frequencies, confirming that the signals contains only single frequency component. This demonstrates the effectiveness of FFT in identifying signal frequency. Task 4, signal combination. For task 4, we combine two different signals. The first signal was the original sine wave, while the second signal was square wave with the same frequency. The two signals were added together to form a new combined signals. After combining them, we analyze both waveform and its frequency spectrum. Slide 8. Combine signals into domain. This slide shows the time domain representation of combined signals. The upper graph displays the original sine wave and square wave. The lower graph shows the result signals after addition. We can observe that the combined waveform is no longer a pure sinusoid. The square wave introduced sharp transition and sudden change in amplitude, causing the waveform to appear more distorted. This illustrated the principle of superposition, where multiple signals are added together. Slide frequency spectrum of combined signal. This graph shows the FFT results of the combined signals. The largest peak remains at 2 kHz because both signals share the same fundamental frequency. However, additional peaks now appear at higher frequency. These peaks are harmonic component introduced by the square wave. The harmonic occurs at odd multiple of the fundamental frequencies such as kHz, 10 kHz, and 14 kHz. This demonstrates how complex signal contain multiple frequency components. Slide 5. Adding AWGN noise. For task 5, we added additive white Gaussian noise or AWGN to combine signal. The signal to noise ratio or SNR was set to 15 decibels. AWGN is commonly used to simulate real communication channel noise. This allows us to study how noise affects signal's quality during transmission. Effect of AWGN noise. This graph compares the original signals and the noise signal. The purple line represents the original signals, while the gray line represents the signal of the noise was added. Although the overall waveform shape remains recognizable, random fluctuations are clearly visible. This shows that noise can distort the signals and reduce communication quality. The experience highlights the importance of maintaining a high SNR in communication system to ensure reliable signal transmission.